Hello everyone, I'm going to present a new method to create volumetric rocky details in virtual terrains. First, I will give you some context about our topic and the problem we are trying to solve. Virtual terrains have been around for many years now. They are a key component of natural scenes, with applications in the entertainment industry as well as the scientific simulation software. Terrains have this particularity that they have a multi-scale structure, and they are made of both planar and volumetric features. In this paper, we focus on volumetric terrain modeling. Before going through previous work, let's see exactly what we are interested in. We heavily base our work on geomorphology, which is the field that studies earth processes and landforms. One useful thing that they do is that they classify earth landforms based on various criteria. Here is a picture to illustrate this. The first thing you probably see here is the macro-scale features, which are the two big arches. The second layer is the mesoscale features that you see here. If you look closely, you will see different block structures emerging from the cliff face. The final layer is the high-frequency microscale details. These three layers of scale contribute to the realism of the virtual scene. What we will see in the state of the art is that there are no method or model to represent all these different scales of features. The first research area related to our work is terrain modeling. Height fields are the most common representation both in industry and research. However, this model prevents the creation of volumetric features such as arches and overhangs. Voxel models are generally memory expensive and therefore limited in precision, which forbids the creation of multi-scale terrains. Recently, implicit models have been introduced for modeling large 3D terrains, with features such as karsts, sea caves, and hoodoos. While this model can theoretically reproduce highly precise geometry at a low memory expense, existing work only relies on noise for the mesoscale and microscale details. In this paper, we extend this implicit model and introduce new primitives and operators for mesoscale and microscale features. The second close research area is volumetric texturing. Hypertextures and generally all noise-based approaches can produce high-frequency details. However, they cannot capture the characteristic patterns of the bedrock. Discrete element textures can synthesize distributions of objects from exemplars, but there is no guarantee to obtain geologically correct block structures. Finally, textile mapping can produce volumetric features, but it requires an explicit parameterization of the surface, which we don't have easily when working with implicit surfaces. There are other methods to add details to terrains based on mesh decoration. A periodic rock tiling was introduced to create rock piles commonly found at the bottom of cliffs. This method doesn't follow a fracturing model and therefore fails at generating certain types of blocks. The ghost-style approach can be used to create entangled tiles of objects from 3D models. This work does not address the synthesis of block structures. With all that said, let's recap our approach, motivation, and present our contributions. We want to synthesize meso and microscale details for volumetric terrains. We will focus on the implicit model introduced in previous work. Our technical contributions can be described as follows. First, a geologically-based method to synthesize block structures for the meso and microscale details. Second, an implicit replication operator for placing and blending blocks while keeping control for the user. Now let's get into more details about our method. Our goal is to synthesize realistic block structures. Different block archetypes have been identified in geomorphology. These types are all visually distinct and are formed under different environmental conditions. The main difference resides in the variation of fracture distributions. A fracture is a break of continuity in a body of rock whose origin is natural. It most frequently occurs as fracture sets, and these can be analyzed based on their orientations, spacing, and physical properties. For example, regular and axis-aligned distributions of fractures result in equidimensional blocks, whereas randomly distributed fractures produce a polyhedral type of block. We will use these differences in fracture distributions to let us synthesize different block structures. Our method works as follows. We first generate a set of tile embedding blocks based on a geomorphological classification. These blocks represent the meso and microscale volumetric details of the terrain and are implicitly defined by a specific scalar function. The second step consists in amplifying a smooth input terrain from user-defined information by replicating blocks over the vertical parts of the bedrock. The output of our method is a detailed 3D terrain defined as an implicit surface, whose scalar fit function is a construction tree combining the input terrain and the different block functions. We will first talk about the tile generation process. In this section, our goal is to synthesize detailed tiles of blocks for the meso and microscale features. The tile generation process works as follows. First, we distribute samples inside the cubic tile C and compute the geometric nearest neighbor graph G, which is not represented here for clarity. Then, we generate a fracture distribution and cut intersecting edges of the graph. This distribution can be of any type, polyhedral, equidimensional, etc. At the end of this step, we get clusters of points Gi, which are just subgraph of the initial graph G. Finally, we extract implicit convex primitives and create a scalar function for each block in the tile. Note that only one step of the pipeline changes based on the type of block that we want to create. The remaining question now is, how do we distribute fractures so that blocks will have the desired shape? We have specific rules for distributing fractures in the tile. In our method, fractures are represented as 3D disks. We first distribute fracture centers and compute fracture orientations based on the desired block type. They can be axis-aligned, following one main direction. They can be tilted or even computed randomly in the case of polyhedral blocks. These fractures are then used to remove the intersecting edges of the graph. This is performed using a simple segment disk intersection test. More formally, assuming 2 points were connected in the initial graph, they remain connected under the following condition. At the end of this step, we perform a float fill algorithm to get all clusters of points Gi. Recall that our goal is to create implicit primitives for representing the meso and microscale details of virtual terrains. From the previously computed clusters Gi, we compute polygonal meshes using the quick hole algorithm. For each triangle in a mesh, we extract planes HK and create an implicit primitives defined as a smooth intersection of half-space functions associated with the planes HK. Using a smooth intersection operator is mandatory to prevent gradient discontinuities. For this operator, we use the following equation. You may notice that the resulting surface is smooth. It lacks high-frequency details. Adding surface details to implicit surfaces is challenging, as they do not provide an explicit parameterization. To solve this issue, we introduce a new gradient-based warping operator inspired by triplanar mapping already done on meshes. Our operator does not require an explicit parameterization and works with any implicit surface model. It is applied to every block and introduces small-scale volumetric details as displacements that enhance the model. The operator is defined as a warping, with delta transforming the point P along the direction of the gradients. It is itself defined with the following equation. We have g of p being the normalized gradients. The weighting function alpha computes the contributions of the free displacements according to the scalar product of the normalized gradient and unit axis-aligned vectors. D is the function that computes the strength of the displacements, and gamma is the projection of P on the free planes of the cube. The resulting blocks show high-frequency microscale details. The interesting thing is that you have control over the displacement function d, which can be defined as a construction tree, procedural noise, or a baked texture. Our method is capable of reproducing a variety of block structures. These types have been identified in geomorphology and are the result of different fracture distributions. We also provide control to the user, which can prescribe specific blocks in the tile. Here you see an example of tabular and rhomboedral blocks manually placed by the user in an equidimensional tile. The fracturing process adapts and synthesizes blocks all around the user once, creating a tile with two types of blocks. Here we compare our work to two traditional techniques used to add details to virtual terrains, namely hypertexture and radial displacement. As you can see, and even if noise is capable of producing high-frequency details, we compare favorably in terms of mesoscale structure. The self-similar appearance of noise is not capable of reproducing realistic terrain features. Here is a short performance table for the tile generation process. This step is mostly dependent on the amount of fracture D. As a highly fractured tile will require more intersection tests between the edges of the graph and the disks. However, we did not spend time on optimization, as this step only has to be done once in pre-processing. So far, we have created detailed tiles of different types of blocks, tabular blocks, equidimensional blocks, etc. Now the goal is to amplify a smooth input terrain with these detailed blocks. We aim at generating a modified terrain tilde t as the union between the base terrain T and the replication R of some blocks Bi. We want our blocks to be replicated over the surface of the initial terrain and also on steep cliff faces. Infinite replication has already been introduced in implicit modeling. It works using a modulo operator between P and the size of the tile S. This is useful for lowering the complexity of a scene, as a single operator is used to replicate a model. However, in our case, we want to provide more control to the user and not infinitely replicating blocks in the scene. Therefore, we extend the concept of infinite replication and add control for choosing where the primitives should be replicated. We introduce a parameterized replication operator based on a presence function E that evaluates whether a block Bi should be replicated or not. An anchor point is used to evaluate the presence function E. Using this formula, a block is replicated if and only if its anchor points satisfy E of AI is equal to 1. The interesting thing with this formula is that the presence function can be any combination of a variety of criteria, such as distance to the surface, steepness of the terrain, or even bedrock material type. I will now show you some of the result of this replication operator. Here is a volumetric coastal scene made of an arch and overhangs, amplified with equidimensional blocks. You can see the initial terrain T at the bottom left of the screen. Here is the same scene amplified with rhomboedral blocks. and finally with tabular blocks. Here is a comparison between the Arches model, which uses a mix of voxels and implicit surfaces, and our method, based only on implicit surfaces. On the right side, detailed tabular blocks have been replicated on the cliff. To conclude, we presented the first multi-scale model for 3D terrains. We extend the implicit model introduced last year with specific primitives and operators for representing the meso and microscale details of the surface. We created a method to synthesize geologically correct block structures of different types. And finally, we presented a new replication operator for blending blocks with the base terrain. As future work, we could extend our fracturing method to model other types of blocks, such as columnar ones. We also plan on investigating global fracturing methods over an entire terrain, which would create large-scale fractures. Finally, we could optimize our blocks primitives and investigate their implementation on graphics hardware. Thank you for your attention and feel free to ask me any question.